Hello, high water viewers, and welcome to today's video. Today we're going to be jumping back into Unity. We're going to be following up on our previous video on modeling fluids and tanks. And today we're going to be looking at tank drainage. In our previous video, we set up the system for filling tanks. So as an example, we could fill our tank. In this case, this valve is one half of a cubic unit per second. We could do twice and get twice the flow rate. We can shut it off halfway, shut it off completely. And this one is 3 cubic meters per second, or cubic units, and we can double that again. So you can see we've set it up so that we can model how to fill a tank. Today we're going to be talking about how to drain a tank. Now, there's quite a bit of a difference actually between filling a tank and draining a tank. If you watched our previous video, we may have talked about that some. When we fill a tank, we assume, or at least in this case we were assuming, that our tank was connected to some kind of municipal water source, so we're able to provide a constant flow rate. I mean, we can change our flow rate, of course, as we did with the valves, but we maintain a constant flow rate otherwise, right? It's not changing over time. Let me go ahead and close that. When we are modeling tank drainage, the rate that the tank drains is dependent on the fluid level of the tank. Now, we have a whole nother video on in preparation for this video. We did a video on the mathematics of tank drainage, how to set up the mass balance, how to set up the differential equation, solve the differential equation, and basically get a solution that we're going to use in this video today. We're not going to go back through the math again because we've already done that on sort of a blackboard type of video, but today we're just going to be looking at how to implement this into Unity. Just looking over my notes, make sure I talk about everything. So one thing I do want to look at or talk about today is that if you watched our other video, we've made a few changes in how our code is structured. The last time we were kind of just slapping it together because we were only really interested in the fluid mechanics. We weren't really interested in best coding conventions for Unity. I've kind of cleaned that up some. We moved everything that's ray casting or any sort of input queries into our player controller. We also now have separated, because we have different types of valves. We have influent valves, supply valves, right? We also have the drain valve, obviously. So we've split this up to accommodate both types of valves, depending on which layer it's on for the raycaster that intersects it, impacts it, whatever the word is there. And if we're not getting any sort of successful raycast, then we just shut everything off. Basically, there's no hit, and we shut off our overlay, which is controlled over here in our display or hide overlay display controller. And our valve script now, is where we used to have a lot of our code for controlling things, which didn't really make sense. Now it just holds a flow rate so that we can set different individual flow rates as member variables on different valves. Influent valves, actually. This has nothing to do with the drain valve because, of course, the flow rate is not a constant like this. Okay, so I think that's it on that. The only other thing I'm going to want to say in this introduction before we do a little pause and to save this video is that I'm not doing any live code today. Usually I like to do that because I think it provides a better understanding of the flow, but in this case I just think it'd take too long and I'm going to make probably way too many mistakes if I try to do it live. So I won't. I'm just going to go through and talk about how we set it up and how we made it work and what everything means. So, all right, we will do a little pause on the video here and jump back into it in just a moment. Thanks. Okay, welcome back. So I think before I do anything else, I'm just going to real quick discuss some of the layout here. Obviously, that's our drain valve. This is where everything has a valve script, so there's no difference between influent valves or drain valves. They all have the same valve script. And within our tank, we have our fluid here, which has our fluid controller. So we're controlling the fluid directly on the fluid. And I do want to say that, except for the fluid here and the obvious primitives, these assets that I'm using are from Cinti Studios polygons. I think this one's the Apocalypse pack. So I just wanted to, if you're interested in where I got those, that's where I got them. And yeah, so the only other thing is I believe the first person controller has our player controller script. And I believe that's all our scripts. Well, the canvas has the display, which also has our little reticle. Actually, no, we have two different ones. But okay, so anyways, that was probably not super necessary. But getting into maybe the reason you're here, really all our fluid mechanics are happening within the fluid controller. And we set up in fact, we already had these set up from last time, these serialized fields, which are really just a geometry for the tank. With the one exception, this new addition is the drain area. Now that is assumed to be basically the hole that the fluid is draining out of. It's probably pretty obvious. Now, there's not modeled into this the influence of like a sharp edge orifice or a rounded edge or anything like that. In this case, I'm just assuming that there's no influence there. You're getting 100% flow. There's no frictional loss. Obviously, if you're familiar with fluid mechanics, it's not going to be a challenge to modify that. You basically just multiply a modifier in. You could add another serialized field. But that's not a big deal. Then we have our mesh renderer on our fluid. That's going to basically, I just use that so that I can turn the fluid off and on so it doesn't cast a shadow. That's really all that is. So if there's no fluid in the tank, then I shut off the mesh renderer at the beginning, or if it's ever at 0. So basically if we drain the tank empty, then we shut off the mesh renderer. And then we set up all these private variables that are going to be used within the system. And so that's going to be our flow rate. We're going to calculate based on what all the pipes are adding up to, the influent pipes. So, these guys over here, the sum of how open they are and what their flow rates are going to give us our flow rate. Area, these are pretty obvious, and we go over this actually in the last video, so I don't want to kind of retread too much of that. That's used in the filling of the tank. In fact, actually, let's just kind of jump in, because the rest of this isn't probably going to make sense until we kind of talk about the rest of this. So we set up our tank. This is still, again, pretty much the same as what we did last time, where we are just setting up our areas, all our tank information, and setting up our fluid as having zero height. Basically, there's no, obviously the tank is empty, right? So the height is 0, in this case represented by scale, and we're setting the position of the fluid to the tank bottom, and otherwise preserving the other information there. And then we go into our, do I want to go with update? Sorry, I should have kind of, well, actually everything is pretty much update now. So we have a couple of different possibilities. Basically, the tank is either empty and we start to fill it. because if we're more than 0, right, we're starting to fill the tank, we want to turn on our mesh renderer, because if we are just now starting to fill the tank, it would be false, right? And then beyond that, if we either are filling the tank or we're draining the tank, right? So we're either filling the tank and it is going to fill up to the top of the tank, right? So since these basically fill from the middle, right? The scale is changed. It's grown from the middle of the object. We want to look at half of the tank height, because that's where the transform. Now you can of course do this differently, but in this case the transform's in the middle of the fluid object, so twice the height from the middle of the fluid is going to be the tank height, right? So we want to make sure we're not overfilling the tank, at least how we have it set up. You may want to do things differently. And so if we are filling the tank, then we are going to do it the same way we did last time. Actually, there's no difference in this case. If we're just filling the tank, then basically we are computing the velocity that the fluid surface is going to rise based on the flow rate divided by area. We're going to make that a function of delta time and then use that to modify the height. We did that last time. If you want the details on how we worked through that, I mean, that's kind of, there's not a whole lot more to it than that to begin with, but that's in our other video. So we just basically set the local scale to the height, and we set the position. We modify the position because as this grows, since we are growing it from scaling it up from the center, we need to also adjust the height. Otherwise it grows down into the ground as well, right? So we grow it and then we move it. And that's it. Okay, so that's it for filling. And so now the real reason you're here, hopefully, is for the draining. So we're finally getting to that part. And in this case, we are going to look at the solution to the differential equation that we did in the other video, where basically I don't have my notes on me, and I really don't want to say it wrong. Maybe, you know what? I'm just going to real quick pause the video, go grab my notes. Okay, sorry about that. Thanks for waiting. I think I just really messed up my. Can I get that out of the way? Okay. Okay, so once we've solved the differential equation, we have our height is equal to the square root of our initial height minus a constant times time divided by 2, and then all that squared. That's what this all amounts to. So if you kind of break that down into, what does that mean in reality, the things we're looking at are our initial height. Now the rate that the fluid drains is going to be a function of the height. So the initial height is of course going to make a big difference in how long it's going to take to drain the tank, or really the fluid level at any other time, after initial time. So that's going to be one factor that we're going to be looking at and need to account for. Of course, our time in seconds is going to be a very important aspect. And then our constant, well, this will all be constant, but it is going to matter too. So we have our drainage area, which is, of course, or again, the area of basically the drain hole for the fluid to pass through. And then everything else is just the area of the tank. So basically the ratio between those two, because the velocities are going to be a function of each other, or relative to each other. And then of course we have gravity, the square root of 2 times gravity times drainage area divided by area. So the only other thing here is the drain area modifier, and that is just something I used to zero out the constant, which actually I don't think we're even using anymore. Initially, I had it possible for the tank to be filling and draining at the same time, but it became really complex in managing everything, so I took that back out. And I don't actually remember now. I don't think that's even necessary to have that in at this point, actually, because you're either going to be not draining, right, or you're going to be filling it, or you're going to be draining it. So actually, you could probably leave that out. I apologize for leaving it in. Okay, so then once we have that, really, the height obviously is what we're interested in once we have it. And now, one thing to note is that when we were filling, we're doing this plus equals, right? We're adding the small slice of new fluid material because of delta time, whatever this time since the last frame rate, or the last one before that, whatever, is how much it's grown. We're going to add it to what it was previously. In this case, we're just recalculating it every time and then setting the height to, or the scale to the height. And the reason we're doing that is because it matters. Basically we're calculating the whole system as one evaluation over time. Like, we're starting with an initial height, and then we're calculating what it will be at any other time after that, and working through that change in time instead of calculating it as a delta time, over and over again each slice. We're doing it all as one. And then we're just doing the same thing where we're resetting the position. And other than that, since we are setting it equal, did we do that here too? Yeah, so in both cases, we want to preserve what the original positions and scales in the X and Z directions are. We don't want to change any of that. We're just changing the height. And then, since we're draining, I set it to where once the height gets down to 0.001, basically just shut it all off. Consider it drained. So I'm going to set a new vector 3 for the local scale where the height is 0. So basically, it's there is no height. Of course, we don't want to change this X or Z. And then just actually setting the height to 0, and then shutting off the mesh renderer so it doesn't cast a shadow, and then closing the drain. All right, so that's really all the fluid mechanics. The only other thing is handling all this stuff, where you either have drains opening or closing, which are the influent drains, which are these drains. So you're either opening those, in which case you're going to be adding their flow rate that's going to be passed in when you open the valve, based on information that's on so that is actually that's our valve script here, right? So it's going to get passed in when we open the valve, and because, is that from here? Yeah, so right, because we get it from the raycast on the object that we hit. We get that component from the valve script. We pass it through. Although we're actually, that's the drain. Yeah, open valve from here. And then, so we change our booleans, is filling or is draining. We reset our time to 0. So this is where it gets a little bit important, in how I was making this work. Because every time we change, and actually it doesn't matter now with the influence, because they're never going to be on while it's draining anyways. But when you open or close the drain, you need to reset the time in seconds and the initial height to the current height, because basically anytime you open that drain, you are starting the evaluation. so to speak, because you can consider that time 0. We just now started to drain it, right? So our time in seconds at that in that instance is going to be 0. That's our initial condition. And then our initial height is whatever the height is when we open the drain, right? That's our initial height. So anything after that is we're going to have this draining. It's going to be, decreasing because we have our initial height. This isn't going to change, but our constant, really the only thing changing is the time, right? So as time increases, we are subtracting that from our initial height. And of course, since it's going up and being recomputed every frame, this is going to be decreasing over time, right? And which is exactly what you would expect. This is exactly the solution to the differential equation. So over time, the amount of change in the fluid height, the rate that it's draining, is going to decrease for the same time steps. And then, of course, closing drain, we just do the opposite. We set reset the time, and then initial height. Probably don't actually really need to do that, but if you were to combine these flows back together, where you would put the flow rate in here, basically, then you would want to include all these things. And the only other thing is if the flow rate goes negative, then we set it to 0. And that's it. Okay, I think, really. I don't think I'm missing anything here. No, I think that covers it. So, if you have any questions on this, I know this is kind of difficult, I think, probably to sort of jump into code that's already written and try to explain it. It's a little, I think, harder for me to explain in a way that makes, a lot of fluid sense. That wasn't meant to be a pun, but easy to follow along with. So if you do have any questions, just let me know, and I'll do my best to try to answer those. And either way, we really appreciate you stopping by. I hope this was something that was helpful to you if you're interested in modeling fluids in Unity. And of course, we are still starting out. We're starting to actually gain some traction, and it's getting kind of exciting to be, in this new channel. But if you do want to help get the channel off the ground, be part of the community, a subscription is super helpful. And of course, if you want to leave a comment, we'd love to hear them. And that's it. I think we appreciate you coming, and I hope you have a great day.